Welcome everyone to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating AI research. We're looking at a paper called MonSter, Marry Monodepth to Stereo Unleashes Power. Essentially, it tackles the problem of figuring out depth from images, how far away things are. Existing methods using stereo matching, that's like using two cameras, often struggle with difficult areas. Think occlusions or textureless surfaces. So MonSter proposes a novel way to combine the strengths of monocular depth estimation, that's from a single image, with stereo matching. They use a dual-branch architecture where these two approaches basically help each other out iteratively. And while the results seem pretty strong, ranking first on several major benchmarks. So speaking of strong results, this first figure really highlights one of MonSter's key strengths. It's zero-shot generalization. What we see here are some examples from the KITTI dataset. The top row is the input image. The middle row shows the depth map from a baseline method called IGEV, and the bottom row is MonSter's result. Now, these models were only trained on scene flow data, not KITTI. You can see, especially in those tricky areas marked by red boxes, think reflective surfaces, distant objects, or fine structures like fences. MonSter produces much cleaner and more accurate depth maps compared to IGEV. It really shows how combining mono and stereo helps handle those problem areas, even on unseen data. Building on that idea of handling tricky areas, this next figure digs into how MonSter actually aligns the monocular depth estimate it uses. We're looking at how well the disparity derived from monodepth matches the ground truth disparity here. You can see that without any alignment, it's pretty scattered. Even if you just apply a global scale and shift, like in the middle plot, it's better, but still quite noisy. But the key thing is the plot on the right that shows MonSter's refinement using per pixel shifts. Look how much tighter those points follow the red line. It means the alignment is significantly better. So this detailed, per pixel refinement really unlocks the potential of that monocular prior. Okay, so building on that alignment idea, this next figure actually lays out the whole MonSter architecture for us. You can see the two branches we talked about, the monocular depth part processing the left image up top, and the stereo matching part using the image pair down below. What's new here is seeing they actually share the same initial mono encoder, which is pretty efficient. Then, after that global alignment step we discussed, which converts the relative depth to metric disparity, we get to the core refinement loop. This shows the stereo-guided alignment refining the mono shift, and then, symmetrically, the mono-guided refinement using that improved mono depth to fix up the stereo disparity. They iterate on this a few times, helping each other out, before outputting the final depth map. So we saw the architecture and how those branches refine each other. Now this figure gives us a look at some qualitative results, this time on the ETH3D dataset. Again, we have the input image on the left, the baseline IGEV in the middle, and MonSter on the right. These are pretty challenging scenes. Look at the strong reflections on the statue in the top row, or the thin structures like the table legs and pipes below. You can really see where the white arrows point. MonSter just handles these tricky areas much better, producing smoother and more accurate depth compared to IGEV. It really reinforces how that mutual refinement helps in tough spots. So we've seen the architecture and some nice qualitative examples. This table now really breaks down why it works so well. It's an ablation study on the scene flow test set, basically testing how much each piece of the MonSter puzzle actually contributes to the final result. You can see the baseline IGEV starts with an error, that's EPE, of 0.47. Adding the monocular depth and the specific MGR fusion method drops that error quite a bit, down to 0.43. Then, adding the SGA refinement step we talked about, that brings the error down significantly again to 0.39. And well, the full model with feature sharing gets the best EPE of 0.37. So this really confirms that those key refinement modules, MGR and SGA, are super important for getting these strong results. Okay, so that ablation study really drives home how each piece helps build the final performance. I think the big takeaway from MonSter is just how powerful it is to combine these two approaches. Monocular depth and stereo matching. They really do help each other out, leading to much more robust and accurate depth, particularly in those difficult areas we saw. And this idea of fusing different methods, it's really important for advancing computer vision for applications like robotics or augmented reality. Well, that wraps it up for today. Thanks for joining me on the AI Research Roundup. I'm your host, Alex.